All right, let's resume. Andy will talk about gradient properties of RG flows.
Thanks, Balt. Let me start by thanking the organizers for a very nice meeting and also for the opportunity to speak. So this will be about gradient properties of renormalization group flows, and it's based on a paper that appeared a few months ago in the archive with my student William Pannell, who is somewhere in the audience, up there. And it's a project that sort of grew out of discussions last year at the meeting in Brazil with Slava, and also when we were working on it, we benefited a lot with by discussions with Hugh. So the setting that we will be focused on is that of relativistic and unitary perturbative quantum field theory. Nothing I will say today will be non-perturbative or bootstrappy, so everything will be rather confined to a specific set of models in perturbation theory, but perhaps the lessons learned will be more general. And the standard sort of picture we have in mind when we discuss renormalization group flows in this setting is that we have some ultraviolet CFT. A lot of the time in the perturbative setting, this ultraviolet CFT is free, but it doesn't have to be. And we perturb this by some relevant operator, and this starts some renormalization group flow, which we describe by some renormalization group time, which is minus log mu, which increases as we flow towards the IR. And then that's not the only option, but one popular option that we like to analyze is that where we have an infrared conformal field theory that we end up in. Okay? Now, this is a very simple picture, and it's of course a cartoon, but the question is, what are the possible endpoints of this RG flow, and can we make general statements that constrain what they might be? Okay? For example, could it be that you start from some UV CFT, and then you perturb similarly, but then when you reach the IR, maybe you go to something like, a limit cycle or something like this. Could this happen? So could this be a possible endpoint for an RG flow? And there was speculation from the early days of the RG by Wilson already himself about possible endpoints of an RG flow that look like limit cycles, or that might look like ergodic behaviors, where the RG flow stays in some region but never reaches a fixed point. Now, it's not hard to describe solutions that might look like this. Now, from a fixed point of view, what we say is we introduce a beta function that will describe sort of the speed of this RG flow, and then for a fixed point, we ask for that beta function to be 0. In general, the beta function, if we have a set of couplings, remember this is all perturbative, so these couplings are the couplings with which the deforming operators of the UV CFT are added. And there can be many of them, so maybe you can give an index here. Now, if this is 0, you will get a fixed point, but there could be solutions, for example, where this is something like this, where this Qij is some constant antisymmetric matrix. And if that's true, then I can just exponentiate this and see that the couplings will go on in a cycle. Okay, are there such solutions? That's the question. And you want to make, they have never, let's just say they have never been found, although with some qualifications they have, but such solutions where described cycles in the normalization group have never been found, and we want to make statements that, show that they will never be found. And usually these statements amount to monotonicity theorems. the more popular of those, is the C theorem in 2 dimensions, proven some time ago by Zamolodchikov. But they come generally in different flavors. And there is the strongest monotonicity theorems, which tell you in this perturbative setting, that the beta function is gradient, in that there is some metric that you can think of as a Riemannian metric. It's symmetric and positive definite, so that I can invert it and bring it over to this side if I want to, and a scalar A such that the beta function is written in this way. And if that's the case, then you cannot have cycles or things like that. The RG flow will be very simple. So this is the strongest version of monotonicity theorems. You could call it the strongest version of the A theorem or the C theorem. And then there is the strong version, which tells you that there exists a quantity A that is monotonically decreasing. Okay? So the strongest version tells you that there is, maybe I should say here that this metric over here should be Riemannian. The strongest theorem, of course, implies the strongest version implies the strong version, but the strong version just asserts that there is a quantity A, scalar quantity A, that monotonically decreases in the flow to the IR. Okay? And this quantity can then be sort of thought as a measure of the degrees of freedom of the theory that are sort of lost. The number of them decreases as you go towards the infrared. And then there is the weak version of the A theorem that says that there is some quantity that is bigger in the UV than it is in the IR. And the endpoints here are sort of assumed to always be conformal field theories. Okay? So these are the 3 flavors of the A theorem, or in general of monotonicity theorems. And of course, this one has been, in 4-dimensional quantum field theory, a very nice chain of arguments by Komargotsky and Schwimmer that eventually proved it. It was originally suggested by Cardy that the coefficient, this A, should be the coefficient of the Euler term in the trace anomaly, and eventually that was found to be correct. The strong version has never been in 4-dimensional quantum field theory has never been proven non-perturbatively, but Hugh Osborne has a perturbative proof around the free theory, and in fact, in conformal perturbation theory around any theory, that the strong version is correct. And the strongest version is what we will be discussing today. In fact, Hugh has a proof that perturbatively this is true, but not necessarily for a Riemannian metric, but for a metric that might have an antisymmetric part. So today, I will be focusing on the question of the strongest version of this monotonicity theorem, but for a Riemannian metric. Yes? Yeah, I'll talk about 4 dimensions today and also 4 minus epsilon, and you can expect these statements to also make sense in fractional dimensions. Yeah. Okay. Now, unfortunately, I won't be able to answer this, question if the flow is gradient in some full generality in 4 dimensions, but I will be looking at a specific theory . So this is some standard phi to the 4th theory. It contains all of the phi to the 4th theories because I allow for this tensor coupling lambda, the deforming operators to be added, all sorts of combinations of them. And here, the only constraint I impose, of course, is that this lambda tensor is symmetric, and then I add this deformation. And what we want to say is that in this setting, there is a beta function associated with this whole tensor, and the question is that beta function gradient or not? Okay, so everything will be for this theory. It's not one theory, it contains, of course, a lot of examples, and we want to see if this beta function is gradient. So I will denote this collection of indices still by I, J, capital J, and I will not write them all down typically, although in some cases I will. So we want to see if this beta I can take this gradient form where repeated indices are summed over, and I'm not worried about the placement of indices here, for some g that I will simply have to find. It's up to me to find this g, and some a, which is a scalar, that I will simply also have to find. And this g over here will satisfy these constraints that it's positive, definite, and symmetric. And why do I need this extra constraint? A nice thing about it is that if I have, so if Gij is symmetric, then I can go to Riemann normal coordinates around any point, and essentially then at any point in coupling space, I can write Gij as essentially the flat metric. Around that point, of course, I will have order lambda squared corrections, but at any point I can make this choice. And when I make this choice, then from the basic equation, I have that the beta function is then just the derivative of a scalar. And then this implies that this matrix is symmetric. And this matrix being symmetric means that its eigenvalues are real, but these eigenvalues are related to the dimensions of the deforming phi to the fourth operators. So if I have this property, then I'm guaranteed that at real fixed points, unitarity will be maintained. Okay? Which otherwise, you know, you don't get a symmetric matrix here. This isn't necessarily symmetric, so you have no argument as to the effect of, you know, preserving unitarity at a fixed point, at a real fixed point. So this was one motivation. I don't consider it a very strong motivation, but it's one motivation to focus on a metric that is symmetric and positive definite. Okay? Yes? Yeah. But, you know, there are some non-unitarities in some, you know, high-dimension operators involving, you know, that are evanescent operators that disappear in integer dimensions, and this is not expected to affect any of the phi to the fourth like operators in which the RG flow is defined in this context. So the RG flow here is constrained to the subspace of couplings of phi to the fourth like operators. And in that subspace, there isn't going to be any non-unitarity by being in fractional dimensions. More generally, one has to. No. Okay. So this is the equation. This gradient equation is what we want to analyze. And the beta function is something that's computed. Someone can, you know, just compute it in perturbation theory. But this Gij, this metric, and this A is up to me. I'm not trying to compute it. It's just up to me to write one down that works. Okay? So let's start with one loop. So the situation here is very simple. The beta function at one loop. Let me write it down with the indices. So it's, oops, it has the following form. Plus permutations. So it has lambda ij mn, lambda mn kl, and then two permutations where the, you know, you have ik jl and il jk. And I will be using this notation for the one loop beta function to denote this contraction over here. And then obviously I can exhibit an A that works. I can take A to be something like this. And when I take a derivative of this A, what I'm doing is I am removing a vertex and I'm opening it up. So if I remove a vertex and open this up, it's going to look just like this. So I don't need a metric to do anything non-trivial. So this metric is going to be just delta ijkl mnpq, which I can denote by just 4 lines. It doesn't do anything but relabel indices. Okay? So it's trivial at one loop. Have one contribution to the beta function. Here's the A, here's the G, and the flow is gradient. Of course, it's not unique because I can rescale things, but the point is that I can do this. Okay. So that's nice. So let's go to 2 loops. At 2 loops, so now we'll put an index 2 on the left of anything. That means that it's corresponding to the 2 loop thing. There are 2 contributions to the beta function. There is this one, which is a vertex correction. It has some coefficient here. Let's call it B2. And then it has some other correction that is the wave function renormalization correction. So these are the 2 diagrams that you have at 2 loops for the beta function. And now you say, okay, what can this A be? Now there is more freedom. This A can come with there's a diagram like this, and then there is another diagram that looks like this, and then there is a third diagram. Oops, sorry. That looks like this. So there are 3 possible diagrams you can write down. And for the metric, there is a contribution that's non-trivial now that will give it a coefficient that will look like this. It's linear in the coupling, and it will look like this. It has 8 indices, just like before. This one is a scalar. So now the question is, start to take a derivative of these things and use this metric if you need to. There is a contribution delta ij at the leading order to accommodate these coefficients over here. Now, obviously, if I take a derivative of this, all vertices are equivalent. It doesn't matter which one you hit. And if I take a derivative of this, I'm going to open up, say, this one, which means that I'm going to get a diagram that looks like that. Okay? And that's a unique way to get a diagram that looks like that. Now, if I hit a vertex here, they're all equivalent again, I'm going to get a diagram that looks like this. And in dimensional regularization in MS bar scheme, such diagrams have 0 coefficient. That's why it didn't appear in the beta function. But I'm not throwing that equation away. I will need to keep to satisfy such an equation still. But for now, I'm solving this equation in MS bar scheme for the beta function. And well, you can check later that the statements I make are scheme independent. But for now, that's the beta function I have in mind. And if I take a derivative of this one, again, all vertices are equivalent. So whichever one I hit doesn't matter. And I will generate something that looks like this one over here. So obviously, you're going to get 3 equations from this. Okay? The number of equations is the number of inequivalent vertices that you have in these diagrams. And so you get 1 from each. You get 3 equations. You have these 3 unknowns over here to solve for. You have an extra unknown if you want. This one can go and multiply the one loop diagram and give you a structure that looks like one of these 2. But it turns out you don't need it at this order. You can set it to 0, and you can still satisfy these equations using these coefficients over here. So the flow at 2 loops is gradient without the need for a non-trivial, non-globally flat metric. So the metric can remain globally flat. You don't have to make it globally flat. You can choose it to be anything you want and still satisfy the equations. Okay? So at 2 loops, the flow is again gradient. Yes? An extra. No, but the wave function normalization corrects the 4-point function, right, in this way. So you have to include it in the beta function. Yes, and they receive. They do. Yes. Well, you call that the anomalous dimension. Maybe I don't understand the question.
No, but physically what's happening is that you're doing an RG step. So you're going to get some Z. If you acquired some Z, then, yeah, the mic. You do an RG step, you generate corrections to the couplings, you also maybe produce some Z. At this stage, you can always rescale the fields and remove Z, and so you're just remaining with the corrections to the couplings, and that's the thing that we're discussing here. So you produce Z at some intermediate steps of the RG, but then you rescale it away so that you're just left with the correction to the coupling. That's convenient to do.
You maintain your canonical kinetic term that way, and you have your... Let's just say there is a scheme where what I'm saying is correct. And then later I will show you that it's scheme independent. So you can do the calculation any way you want. For me, it doesn't change anything if I set these things at this level to 0. But the beta function certainly includes, if you do the calculation in, say, dimensional regularization in this around the free theory, you will certainly get there's no beta function for Z. That you call the anomalous dimension, and you...
No, but if you introduce that Z as an extra coupling, it will be a redundant description. So there are some couplings in RG description. We talk about some relevant, irrelevant, and sometimes we also talk about redundant perturbations. So that would be, in the language of RG, a redundant perturbation. So you can talk about this, but you can always move it away.
Maybe just another comment. Maybe it's a bit controversial, but I don't think you even need to introduce wave function renormalization in, say, phi to the 4, unless you are insisting on computing renormalizing correlation functions of phi. You don't need it. You could do the same calculation, just subtract only compute vacuum diagrams, make sure that those you subtract divergences there, and then you would get the same beta functions. So you don't have to do. You can treat it just as a conformal perturbation theory, I think.
Sure.
So maybe I'm not connecting dots right. But as far as I understand, your couplings are only lambdas, right? So how does it goes beyond the local potential approximation, for which we already know the gradient, we know the function A, we know metric, we know everything?
Yeah, as I said, I am looking at the RG flow in the space of couplings of classically marginal operators. That's the only thing I can do perturbatively. If I want to go to some, irrelevant, to include irrelevant operators, or I cannot do this in perturbation theory. Certainly they're there, but I cannot analyze them with perturbative methods, and I will be constraining, my RG flow to lie in the space of classically marginal operators, and this will be the setting. I'm not looking at irrelevant operators, what happens with their couplings. I cannot do that perturbatively.
Yeah, but what I mean, maybe I'm recalling it wrong, but it's already analyzed for when you just use local potential approximation, you know everything. You know gradient flow, more or less.
No, Kokolia, that's a bit of a fringe result. It would be a little bit. So there is some function in the function. There's some juggling involved. So there are some papers out there which did an FRG study in local potential approximation for a single field, and they found some gradient flow and so on. But this tells nothing, because that was some uncontrolled approximation to full RG. Here we are doing some controlled, honest-to-God, multi-loop expansion. So this is what one is supposed to do.
Yeah, everything I say here is perturbatively controlled. Various people do various things, so yeah. But this is going to be perturbatively controlled. I'm going to try to keep it that way, yeah. Sorry, say again? Of course. I am simply not assuming anything about how many fields I have here. I'm doing the most general thing, and that will give me a set of constraints that will be most generally obeyed if they are, but there might be redundancies if you have a theory with fewer couplings than you could potentially allow. For example, in ON theory, you have only one coupling, and you don't have to worry about anything I say, because of course you can always write a perturbative polynomial in one coupling as a derivative of another perturbative polynomial. The question is, if you allow the most general structure, is the flow still gradient? Okay. Okay. So now at 1 and 2 loops, this is sort of easy to see. But what you can do is now you can sit down and count how many terms you have in the beta function as you go up in loop order. So this was 1 loop, 2 loops, 3 loops, and we will go up to 6 loops. So in the beta function, we have 1 term at 1 loop, and everything is 1, very easy. We already saw the 2 loop result. We have 2 terms in the beta function, and we had 3 contributions to this A. We had 1 contribution to the metric, and we had 3 equations. So clearly, it seems like we have enough freedom here. Oops. Here to make it happen, to satisfy any equations. Now when you go to 3 loops, it turns out that there are 7 contributions to the beta function. There are 5 diagrams like this. There are 7 contributions to A, and there are 10 equations you get. So again, it seems nice that you can satisfy them. When you go to 4 loops, you have the following numbers. You have 23, 17, 18, and 36. And here is the first sign that something might become interesting, because 17 plus 18 is not quite 36. So there might be some tension. But you may say, well, there are some undetermined parameters here from the lower loop order. I might be able to use them to, satisfy the 36 equations. But even that hope goes away very quickly, because when you go to higher loop order, you get a lot of equations And by the time you get here, you have 571 diagrams. People have computed them. And you have 819 equations. So by this point, it looks completely hopeless that the flow will be gradient, in the sense that you will not have enough freedom to solve the equations that you need to solve for the flow to be gradient. So first, so people have computed up to the 6-loop beta function. That's not me. That's much more well-qualified people. There was a recent, well, for the ON model at 6-loop, there was a paper by Kompanietz and Panzer who did this work, and then a paper by Bedniakov and Pickelner who took the results and sort of decoupled them into all the different structures in this lambda I JKL couplings that you have. So we will be using their results to test the gradient property up to the 6-loop order. I think up to the 3 and 4 loop order, of course, there were earlier results, and the 5-loop result has been known for a while. Okay. These days, we also know the 7-loop beta function in lambda phi to the 4th, but the job of decomposing it into the different structures hasn't been done yet. But once one does that, one can write those numbers down and try to see if the flow is gradient at 7 loops, but I will stay to 6 loops today. Okay, so up to here, we showed that you don't need a metric. The metric can be globally flat, and you can write your beta function that way. Now, when you go to 3 loops, things change. And let me write the diagrams. There is a diagram that looks like this. So these are the things that contribute to A. And already from this, you see that now you have a different thing that's happening, in that not all vertices are equivalent. So now what might happen is you might hit with the derivative one of these vertices and generate a structure that contributes to the beta function. Then you might hit another one of these, you generate another structure, and if those two don't come in with the right coefficients, then the flow will fail to be gradient. Okay? So this one has 3 inequivalent vertices. There is another one that looks like this. So all vertices of this one are equivalent. Then there is, let me write the 5 diagrams that you have in this case. There's no vertex here in the middle. And then there is another one. That looks like this. And this has 3. This has 2 inequivalent vertices. And finally, there is this one. That you should be careful not to draw upside down. Okay? So these are the 5 diagrams you have for contribute to A. This one has obviously only one equation that it's going to give you. So here's how you get, your equations, and you now have the job of checking if, when you take, say, this diagram, you have 2 equations you're going to get out of it. There will be 2 different contributions to the beta function. So let me write them down. So that diagram you can write also in the following way. It's the same diagram. And now you see more clearly that there are 2 sets of inequivalent vertices. When I hit this one, when I hit the middle one, I'm going to get something that looks like this. That will be one contribution to the beta function. But when I hit the edge one, I'm going to get something a little different. I'm going to get something that looks like like this. So these are the two diagrams I get. And these will come with some coefficient. In fact, after you account for some symmetry factors, there is some 1/6 here and some 1/3 here. And then you say, okay, if I have no metric to play with, and I do this, it better be that the diagrams here come out with the right coefficient because they come from the same vacuum bubble. And so this gives you an equation because of this that, let's say, this diagram coefficient must be 2 times the other one. So this coefficient is this diagram, and this coefficient is in front of this diagram in the beta function. And then you say, okay, is this true? And you find, and when you look at the results that people computed, this thing over here is -1/2, while this thing over here is 2. So it's not true. And the flow wouldn't be gradient. Of course, the flow now cannot be gradient without a metric. So then what you do is you allow for this metric that we had before. You allow for this thing to be non-zero, which you could. And now when this thing multiplies a 2-loop diagram, it can give rise to a structure that contributes to this equation. Okay? And that will allow you to fix the problem. And at 3 loops, this is the conclusion that in order for the flow to be gradient, the metric cannot be globally flat. And this was a result that is known since 1974 by Wallace and Zia. It was shown in one of their papers. Okay, so this is already what you see at 3 loops, and then you go to 4 loops and beyond. At 4 loops, there was a paper by Ian Jack who analyzed the 4-loop case. And here you find that there are issues like this that arise, equations like this that arise that not even a metric can fix. And so there are equations that remain that have to be satisfied among the beta function coefficients, that after you use all your metric freedom, after you use all your freedom in deciding what in these diagrams, there's only a few equations left, but they have to be satisfied by the beta function coefficients for the flow to be gradient. At 4 loops, you get 4 equations like that. And those equations can be written in terms of scheme-independent objects. So they are scheme-independent. They are physical, therefore. And you can plug in the values of the beta function coefficients in any scheme that you have it computed, for example, MS bar, and see that they are satisfied. So that's nice. So that was already a result in a paper by Ian Jack and Colin Poole at 4 loops. Then you go to 5 loops, and this is what William and I did. And you find 37 equations that remain after you fix all your metric freedom and all your freedom in choosing what the vacuum bubbles are. You find 37. You plug in, you check that they are scheme independent. You plug in the values that people computed, and they all check out. Now these equations, some of them are simple, but some of them are horribly complicated, mixing loop orders because the metric operates at the lower loop order diagram and brings it up to the order you're working in. So they're very complicated equations that look like they have no chance of being satisfied, yet when you plug in the right, well, the numbers that people computed, they're all satisfied. Yeah. You
mentioned before that there is a possibility that you use some undetermined constants from lower loop orders to do something at higher loop orders. Do you actually need to do that here? So do you fix, for example, some undetermined coefficients at one loop, or?
You don't have to, but you can. It's your choice, what you want to solve for, but you don't have to. Like what I already showed here, where I said you use the metric from the previous order, it's not a unique thing you can do. So you can fix, if you want, some of the lower order things, but you don't have to. There's always.
I'm sorry, I'm not sure I'm understanding that.
There always seem to be, when you solve for the order that you're working in, it turns out that all the other coefficients sort of are on the right-hand side of the solution, and you don't have any equations left over to solve for from things that come at lower order.
So they remain undetermined.
They can. I mean, it's your choice.
I mean, sure, I can send them to 2, but like the equations do not determine them, you're saying.
After you use all the freedom you have in the equations, I'm saying that there will be equations left over that will need to work out on their own.
Sorry, let me put it this way. If you want the beta function to be gradient to 5 loops, does it tell you what is the coefficient of the second structure at the second order?
Not necessarily, no.
Yes
but you
or no?
can make a choice where you fix it, or a choice where you don't fix it, in terms of other things.
Sorry. Do the equation, it's a simple question. Equations either tell you this or not. It's not my choice. Like, equations either tell me what the value of that has to be or not.
No, the equations don't fix all the freedom that you have. That's what I'm saying.
Okay. Thank you.
Yeah, I'm also curious about this point. So one could imagine that indeed the equations don't fix all the freedom, but as you move up higher and higher in loop order, at least the coefficients in lower loop order little by little get being fixed. Like, for example, if you move to 5 loops, maybe at 2 loops some coefficients are fixed, but at 3 loops not yet fixed. So the question is like,
this doesn't seem to happen.
This doesn't seem to happen. So even, well, that's weird.
Yeah. Now, some of these equations are, as I said, very complicated, but some are very simple, and let me show you one. So there is, so let me go to the next one. There are these diagrams in the 5-loop beta function. So there is a diagram that looks like this. So there's no vertices here in the middle. And then so this has some coefficient. And then there is another diagram that has another coefficient that looks like this. Oops. So this is just the vertex. Let me just write it better. So all the vertices are here on the circle. So these are 2 diagrams that contribute to the 6-loop beta function, and they are primitive, which means that they don't have any subdivergency, so you cannot get them with the metric multiplying something from lower order and contributing to a structure that looks like this. And they both come from one bubble diagram, which looks like this. And sorry, this is not good. So there is a bubble diagram that has one vertex here in the middle, and then 6 vertices around that looks like this. So this diagram, when you take a derivative of it, it will give you either this one. When you hit the vertex in the middle, for example, this will open up and look like this. When you hit a vertex, so these 3 vertices are equivalent, these 4 are equivalent. Hit one of these, you'll get something that looks like this. And there is no metric that can save you. So you have one coefficient to accommodate 2 diagrams. So essentially, these 2 diagrams have to have the same coefficient, And in fact, they do. The coefficient here for this is 36 zeta 3 squared for both these diagrams. So the flow is gradient because that number came out the same. And people that work in the evaluation of higher loop diagrams, they have observed identities between diagrams like this that make this happen. And here we see that such identities are also important for the gradient property of the RG flow. Okay, so this is a situation up to 5 loops. And then we went to 6 loops, because why stop at 5 when you can go to 6? And at 6 loops, we got 234 equations that need to be satisfied among the various beta function coefficients. Okay, and now 229 of them were satisfied, but 5 were not satisfied. So now there seems to be a problem, because if all of them were not satisfied, you would say, well, the flow is not gradient, but a lot of them are satisfied, and it's only 5. So let's discuss now what options one has. So there's option A, someone is wrong. And I know some of you at least are hoping for that one. There is option B that says, well, RG flow is still gradient. And there is option C, which is none of the above. Okay, so who is going to go with option A? Now, if you took statistics, you know that you should go with option C because that's the most possibilities. But, some of you like people to be wrong, and that would be option A. And B is a subtle phrasing of the question, because I didn't say that the beta function is gradient. I said that the RG flow is gradient. And if you believe that no one is wrong, then it cannot be that the beta function is gradient, because if no one is wrong, 5 equations are not satisfied, and the beta function is indeed not gradient. So, you see another option, Silvio? Well, many people could be wrong. So I could be wrong. The people that computed the beta function could be wrong. Or all of us could be wrong in how we interpret what the RG flow is. Okay? So these are the options. Sorry? All of the above? Okay. So, I will, the right answer is that the RG flow is gradient, at least to this order that we have checked. But that it's not because anyone is wrong. This is correct. The beta function is not gradient, but the RG flow is gradient. And what I want to discuss, well, unfortunately, maybe I don't have too much time to discuss this, is that how that happens. So when you compute, so these beta functions were computed, in dimensional regularization, and we all learn in our education that when we renormalize, we are supposed to say that the bare field becomes z to the 1/2 phi renormalized, and the z to the 1/2 is a series of poles in epsilon. I add as counter terms, and I determine them by computing diagrams to cancel the divergences that arise. And then what do you do? When someone tells you that this is true, then they tell you that, well, to compute this, what you have to do is go and compute, so this is renormalizes the kinetic term, so you have to go and compute something that will look like the kinetic term. So you say, what's going to look like the kinetic term? At leading order in this theory, you're going to compute this diagram to figure out what 1/epsilon pole has, to then figure out what you have to put here in the 1/epsilon poles to cancel it. But this diagram is not computing z to the 1/2. This diagram is computing z to the 1/2 transpose times z to the 1/2. Okay? Now these are many fields, so this is z to the 1/2 is a matrix. But I have the freedom if this is the identity, to rotate this z to the 1/2 with anything I want. And therefore, I can affect with a completely made up orthogonal matrix what the beta function will be, because this I can do at the level of the kinetic term, because the kinetic term is ON invariant. If this is orthogonal, I can do it. And then I can go to the lambda phi to the 4th term and absorb this rotation by rotating the couplings the other way. Clearly, this is an artificial RG flow that I'm generating that way, and the beta function suffers from it, this ambiguity, and I cannot assign to it any invariant meaning in that it describes the RG flow in some invariant way, because I can simply make up a flow like this when I have many couplings. It's not an issue if you have only one coupling. So clearly there is an issue. Some of you may have already noticed this issue in your education, but I didn't receive a very good education, so I didn't notice it until much later when I started reading papers by Hugh, and who not only outlines this issue very precisely, but also gives the answer as to what is the correct vector field whose RG flow you should be checking. And in order to answer this question, the key observation is to look at something physical like the trace of the energy momentum tensor. Now, what we learn is another equation that is wrong, is that this is beta I OI. Now, this is an equation we also all learn, but it's also wrong. It's not a correct equation because it does not account for operator mixing effects with total derivative operators that might participate in the renormalization of the trace of the energy momentum tensor. In fact, there might be some total derivative term here. Now, this is not a double derivative, so it cannot be improved away to the other side, but there could be dimension d-1 classically operators that after a derivative will participate in the renormalization of T mu mu. And you cannot neglect them, and it happens that in this theory that we are looking at, there are such operators, and they are of this type, where Sij, this coefficient, is antisymmetric, so that I cannot move this derivative outside and make this a two-derivative thing that I can then improve away. Okay? Now, after I use the equations of motion, I can rewrite this thing in the following way, where this bi is the beta function minus this s lambda. So it's just using the equations of motion, which you can do for any conservation or current condition. So this is saying that, well, you shouldn't really be looking at the beta function to see if the flow is gradient. You should be looking at this b function. But what is this s? How do we compute this s? Now, this s is something that you can compute in perturbation theory, just like you compute the beta function, but you have to consider renormalization effects of composite operator correlation functions. So it's not something easy to compute, because when you normalize the field, you normalize the coupling, then correlation functions of operators of phi, any endpoint function of phi, of the fundamental field phi, is finite. But when you consider normalization of correlation functions of phi, including some composite operator, that's not finite. You need to do multiplicative renormalization of the composite operator. And then when you consider correlation functions of multiple composite operators, even after you multiplicatively renormalize each composite operator, that's still not finite. You need to account for what's called operator mixing or additive renormalization. And only then things are finite. An efficient way to do this is to introduce space-time dependent couplings that are sourcing those operators and new counterterms that have to do with derivatives on those couplings. Just like when you go to curved space, you have new counterterms that are proportional to curvatures, which are derivatives of the metric. Here, you're going to have new counterterms that are associated with the fact that you have these sources for operators, and once you normalize the theory with the new counterterms, then taking functional derivatives with respect to the coupling will bring you down correlation functions of finite composite operators. So in this theory, there is a new counter term that looks like this. And I don't have time to go into too many details. So there is a new counter term that looks like this, that will have 1 over epsilon poles. This thing will be expanded out. Into 1 over epsilon poles, and the leading poles of this will give you this S. So this S is like a beta function for this counter term. Which is the 1 over epsilon residues here. So there is a well-defined way to do this computation, but because we have a counter term like this, the diagrams, like at leading order, when you want to compute this, what you have to do is, again, 2 phi's, so you're normalizing the propagator again, but now, say at 2 loops, you need to let momentum come in from the leg because you have 1 momentum here, but then you have to let it come out of the coupling or come out of this coupling. And this way the momentum comes in and out gives rise to different structures for the divergences that you have to subtract, and tells you that this n has to be non-zero. But here S will be 0 because S is antisymmetric, so if I exchange the legs, I have to have a diagram that is asymmetric under exchanging the external legs. And at 2 loops, there is no such diagram. We don't need to worry about this. At 3 loops, there is no such diagram. At 4 loops, there is no such diagram, but at 5 loops, there is. At 5 loops, there are 4 asymmetric such diagrams. And let me write, say, one of them, just to convince you that there is one. So at 5 loops, you have a diagram that looks like this, for example. This participates in the renormalization of the field phi, but it also gives rise to S, to a contribution to this S, because it's not symmetric under exchanging the external legs. So you do this computation, nobody has done it, but you know what the structure is going to be like, and you can add all the diagrams. So at 5 loops, there are 4 S diagrams. And at 6 loops, there are 19 such diagrams. Nobody has computed them, the coefficients, but it's a well-defined computation you can do in perturbation theory. But since I know what the structure is going to be like, I can say, well, I know that the 6-loop beta function is not gradient, but is this B function gradient. I don't know the coefficients, but let me add it in and check if there is a choice of coefficients of this S diagram such that the flow remains gradient of this B field. And when you do this, you find 4 equations that these coefficients have to satisfy. This one, for example, you find an equation that fixes it. So in our numbering, this was S2, and that is something like 259 over 4,608. And that's something that is just predicted by our result, that the flow is gradient only with this choice, and someone now has to do the computation in perturbation theory to see if this is the correct number or not. There are 3 more equations. And at 5 loops, there is no modification, but at 6 loops, you get these 3 equations. One of them fixes the 5-loop contribution, then there's 3 more. One of them involves only 5-loop things, and the other 2 involve 6-loop and 5-loop contributions. Not all of them, but this is the structure of the result. So the answer is that the beta function is not gradient, but the beta function is not the right object to be looking at. And when you look at the right object, which is this B function, then there is a chance that the flow is gradient, subject to a few equations that we found here that if they're satisfied, then the flow would be gradient. But the conclusion, of course, is pending on the calculation at 6 loops of the various coefficients. No, it just so happens that one equation, so we get 4 equations, and one of them requires that this is the case for this diagram. The other ones don't. So there is another equation. I didn't write the diagrams down, but there is another equation that says, 192 times another coefficient plus 384 times another coefficient, which was from another S diagram. This must be 31 minus 36 zeta 3. There is another equation like this. So I don't necessarily fix them all, but I fix that certain combinations of them must satisfy equations. Yep. Yeah, they didn't change anything for those as far as those equations are concerned. So you add them in, and then you say, okay, do they participate in the equations that were satisfied before? They don't. But when you go to 6 loops, they do. And they have a chance to satisfy the 5 equations that weren't satisfied before, become 4 equations that can now be satisfied if the coefficients obey certain equations.
Perhaps I should say, of course, that Ian Jack has calculated some of these diagrams. Maybe not all, but I thought he'd calculated a diagram which gives you that funny number.
Yeah, I think, so, well, you told me about it, so I don't know exactly. I haven't seen it published, but this one was calculated by Ian Jack, and it's correct. This is correct. The number is correct, which means that there's 3 more equations to satisfy. This only involves 5 loop diagrams. The other 2 involve 5 and 6 loop diagrams, so it will be a harder computation. But this one has already been computed in unpublished work by Ian Jack. And it's as it should be for the flow to be gradient. So, so just to summarize, the message is that the RG flow here in these models seems to be gradient. There are still, some conditions to satisfy, but of course, the smart money is that, this will be correct. And, it's a set of conditions that have to be satisfied that is very, very complicated. So it's highly non-trivial that the flow is gradient. It had every chance in some sense to not be gradient, yet it is. So the big question is, of course, physically, why is the flow gradient? There is no physical requirement I know of that the flow should be gradient, but it works in very non-trivial ways. Maybe there is a scheme where you can do the computation where the flow is obviously gradient, and then what I'm doing is just a very complicated check because another scheme implements it in a very non-trivial way. But that sort of remains to be seen. The physical principle or the scheme in which gradient flow is demonstrated explicitly to all orders in perturbation theory has not been found yet, as far as I know. And I should also say that in many other models in perturbation theory, you can do this. By the way, I focused on 4 dimensions, but in 4 minus epsilon, you can do the same thing, and you find that the flow is gradient. There are more conditions that you need to satisfy where you are in 4 minus epsilon. You can do things, in 3 minus epsilon dimensions where you have perturbative control, and then again the flow is gradient. In 6 minus epsilon as well. In all examples I know, the flow always ends up being gradient. You can do it in scalar fermion systems, which is a lot more complicated, and there are relations between beta function coefficients between the quartic coupling and the Yukawa couplings. So it's a highly non-trivial thing that it always seems to work, but there is no principle about why it should work. So that is the main, physics motivation for studying this question, and hopefully that principle will arise in the next few years. Right. Thank you.
There's questions. Yeah.
I was wondering whether one can construct all of the argument based on Polchinski's approach, where, at the price of introducing infinite many couplings, but then you can have exact beta function with only true level and one loop term. Has that been tried? I mean, is any?
Yeah, I think there have been attempts like this. There's a relatively recent paper by Kotler and some, I don't remember the other author, that attempted to do this. But the question is, what is the A function? What is this A? And what is the metric in some sense? And
well, there's an obvious kind of attempt to get some kind of cubic form of function on this infinite dimensional space of coupling, and you can try to then restrict to your set of marginal operators by restricting to a stable manifold of this RG flow.
But you don't want the gradient, the function, that the scalar that you don't want it to depend explicitly on the scale. You want it to be only an implicit function of the scale through the couplings. And I think attempts like you are describing have always involved, I think Slava has also looked at these papers, explicit scale dependence of the scalar quantity on the normalization group scale, which is not something that you want something local in RG scale, that is only a function of the RG scale through the couplings that you are tracking along the RG flow, not something that's an explicit function of.
But I don't think that doesn't sound like an essential problem to me, because if you want to, of course, include all the relevant operators, there's necessarily a scale that goes into this function. But what I was trying to say is that you can then restrict to the stable manifold, which is a finite dimensional subspace of marginal couplings within this infinite dimensional space. And once you have, I mean, that restriction is essentially what kind of automatically sums up this Shrilevant plus one loop to all loop order, right? I would imagine if you do that, then potentially one would be able to define a function that doesn't depend on scale explicitly.
Yeah, maybe you're right. It hasn't been done as far as I know.
Thank you.
I can add a comment. So I totally agree with you with this idea about restricting to the stable manifold, and in fact, this idea also occurred to me a few years ago. As far as there remains a problem to show that the Polchinski equation can actually be written in this form. And in fact, the first place where it is claimed that Polchinski equation can be written in this form is in the book by Tom Banks, in the QFT book by Tom Banks. And also there is this more recent paper by, which Andy mentioned, by Kotler and someone else. Now, both Tom Banks' book and Kotler paper, they actually completely missed this point that this rewriting of the Polchinski equation as a total gradient is only useful if the function that you have, if the potential that you have on the right-hand side and the metric you have on the right-hand side is lambda independent. So in fact, the Kotler paper does rewrite it as a total gradient, but since the potential is lambda dependent, it doesn't prove anything at all.
Mu dependent.
Mu dependent, okay, cutoff dependent. So then you can still have cycles and whatever. Right. So in fact, but it is indeed a tantalizing possibility that perhaps Polchinski equation can be written in this form. It doesn't look to be obvious how to do this. It's an interesting open problem.
Any more questions? All right, let's thank Andy.